Okay, so section 4.2 is titled Newton's First Law. Can we just, is that cool?
Yes.
All right, no lights today? Are we good? Can everybody see?
Yeah.
All right, we got the windows open, that's all right. So, Newton's first law. Now, Newton has three laws that we're going to learn, the forces. I really don't care whether you call it the first law, the second law, the third law, as long as you know that there's three laws. Okay? It doesn't matter. Newton has three laws. It doesn't matter if you call this the first one, the second one, the third one, as long as you know all three laws. Today we're going to look at the first law. On Monday when we get back, we're going to look at the second and third laws. Okay? So, the three things that we're going to do today. First, we're going to look at the correlation between the motion of and the net external force on an object. And I'll explain what net external force means. So looking at an object, again like yesterday, with a force applied to it. The second thing, we're going to be able to determine the net external force. And third, we're going to analyze problems where the forces are balanced. And we're going to call this a state of equilibrium. Okay, that's the three things we're going to do. Oops.
Sounds fun. What?
It does, doesn't it?
Yeah. Sounds like fun.
So,
It would have been better if you played a song to go along with it.
what?
I'm really mad that you didn't play Free Fallin' for us.
I should have, I did.
I really feel like you
So
should have
corny
done-
is good?
What?
I said so corny is good?
Anything to entertain us.
I'll try and think of that next time. Remember the free fall sound? Alright, so Newton's first law says the following. And before you start writing, let me quickly, obviously, first of all, let me make a correction here. An object, it should not say in, it's an object at rest remains at rest. I don't know when I was typing these notes that I had those typos, but an object at rest remains at rest, and an object in motion continues in motion unless acted upon by an outside force. Just the first thing. Asterisks we'll explain in a minute, but just the first definition of Newton's first law. So again, an object at rest wants to stay at rest. Like for example, Steph's textbook here. It doesn't want to go anywhere. It's at rest. It wants to stay there. But if it's acted on by an outside force, if I push it with my hand, then it's going to move. So it's at rest. It wants to stay at rest. Now, the other example is a little more difficult to see. But if I took a pencil, like this pencil here, and put it on my notes, and it started to slide down the notes, it's going to want to continue to move until it hits some sort of a balance point where a force acts on it, and it balances itself out. And that's the example you see in space. And I put up a link in the beginning of the year, and I gave it was an article about what would happen to an astronaut if he or she started floating away from a spaceship in space. How would they get back to the spaceship? So imagine an astronaut is on the outside of a spaceship preparing like a hole. And he's attached with a harness, and for some crazy reason the harness gets disattached. And the astronaut starts floating away from the spaceship. Well, in space, and if you're outside the gravitational pull, you'll continue to float forever. Because there's nothing that's stopping you. Space is a vacuum. There's no air resistance. So if you start floating away, you're going to continue to float away until you get pulled in by the gravitational pull of some planet or some celestial body, like an asteroid. Okay, but by that time, the astronaut himself probably wouldn't make it anyway. But again, if you're in motion, you want to stay in motion.
So if you go out of space and you just jump out of a ship or whatever,
Whatever direction you jump in, you're just going to go out forever.
where you don't die, like your body don't.
Well, sure, you mean you would absolutely die. I mean, if you were in a spacesuit, an astronaut suit, you might last with some oxygen, but eventually run out. Yeah. So you would die before anything else, obviously, but theoretically you would go on forever. That's what's called, which is you could swim. Doing this is not going to help you, because there's no molecules in the air out there. Like right now, physically, if you're in the water and you swim, you move forward, because you're pushing fluid past your body, and that pushes you forward. Right now, there is fluid, but me doing this is not making me go forward, obviously, right? In space, it's even less, because there's no molecules. There's no what's called medium. Space is a vacuum. So doing this, you just be going to nowhere. You need to literally push off something to get yourself to move.
The
And that
magic
is
school
that.
bus really gave the wrong message then, because they were literally swimming through space.
They must have remembered the school bus. And that's exactly what we're going to look at later in the year when we look at collisions and momentum. When you push off and you go separate directions. Steph and then Tom.
What about that guy that saw the news?
Yeah, like I was going to give an example. Very good. So the guy that did the free fall, remember the guy we were talking about the other day? I forget his name. So he jumped from a certain elevation, on like the brink of the Earth's gravitational pull. So when he left the spaceship downward, it continued to pull him toward the Earth. He was technically in outer space, but he was just on the boundary of the gravitational pull of the Earth.
So he only like moved a couple feet or
Yeah, can
something,
we
and
watch
then
it?
was
Watch
So
the
much
video?
now.
If we have time at the end, I did. Guys, I put a link on news. We gotta look at the news articles I put up. There's a video up there. Just for you guys to watch. People don't watch them though. It's up there already. If we have time and we get through the lab example, sure. But it's on news. There's a whole video about it.
What
Huh.
is space made out of?
What do you mean?
Like, what is like the air?
Emptiness. That's why you say empty as space. Have you heard that saying before? Empty as space?
Right.
There's nothing there. It's a
I've heard
vacuum.
that one before.
A vacuum means there's no. It's as empty as space. A vacuum, there's no medium. A medium is like a substance in the air. There's nothing there, literally. So the Earth has certain amounts of molecules in the air, like nitrogen, methane, oxygen. There's different gases, but in space, there's nothing there. It's empty.
Are the molecules like stay around the Earth based on gravity too? Or
What molecules?
molecules? No, the
Well, that's
molecules are around Earth.
Oh yeah, all gravitational pull. Yep. Okay. Now, remember carefully, guys. Remember carefully here. If an object is in motion on Earth, it's going to stop because there's always an outside force. It's friction, no matter what. And think about it. You start to roll a pencil across the table. It's going to stop eventually. Either it hits a wall and there's a forced reaction, or the friction just gets slowed down. An object is dropped and it starts falling down toward the Earth. It's going to stop when it hits the Earth because the force of the normal force is pushing back up. So things on Earth are never going to continue to go forever. That's why that example's tough. But an object at rest, I mean, look around you. Things that are at rest, they remain at rest. Okay? So that's what this is. Now, this is also called the law of inertia, and that's what this next word says. Okay? The word is called inertia. You should write that down for sure. Inertia. This whole thing, an object at rest stays at rest, an object in motion stays in motion, is called inertia. All right. Let's take a look at the next thing we're going to talk about. So, the next thing we're going to look at is called the net external force. The net external force. Now, please don't write anything down yet. You can write the title if you want, but don't start writing. I want to give you an example that makes this a little bit easier to understand before you start writing. So, imagine who wants to be some sort of a salesman. Chaz? What do you want to sell, Chaz? Cars. All right, Chaz, you sell cars. So, Chaz, let's say that it costs the company $16,000 for a car. Let's say it's just a random car, right? And you're able to sell it to the
That's a lot
people
of chicken.
for $23,000. Okay, so the company, it costs the car company $16,000. You sell it for $23,000, and there's also a $1,000 cost of like maintenance and stuff, and the car lot fee. So this is how much money the company has to pay. This is what they bring in. Chaz, what would the net profit be on this sale? What would the net profit be? 6,000, because the other 1,000, don't forget. Again, 23,000 minus this number, which is 17,000, is equal to 6,000. Okay, the net profit or the net gain. So, when you hear the word net, net means take the positives, which in this case, it's a surplus of 23,000 or income. It's a cost here, therefore it's positive and negative, and subtract them or add the two together. Doesn't matter, think about adding or subtracting. It's the same thing we're going to do here. So when you're looking at external net force or net external force, think about the forces that are acting on an object, those that are negative, those that are positive, and just combine them. The same way we just combine net profit. So for this example, another way of thinking about Newton's first law is when the net external force on an object is zero, its acceleration is zero. And let's discuss what that means. I'm just reading what's up here. Sorry, when the net external force on an object is zero, its acceleration is
Should
zero.
we write that down?
You can write it down, or you can listen to the example and see what you'd like to write. So, if I look at this marker here, and I place it on my hand, what's pushing down on my hand, the one of the marker? The weight, which comes from
The net weight.
gravity. The gravitational weight of the object is pushing down on my hand. Now, my hand, as a result, is doing what?
Pushing it back up.
Yeah, it's pushing it back up. And what's happened right now? It's at a state of what?
Rest.
Rest, okay? So, whenever these things are balanced, when these forces are balanced, do you see an acceleration here? So when the net external force on an object is 0, it has no acceleration. Right here, the net external force is 0, because the weight of the object is balanced by me pushing back up. Now, if I take this marker, and instead of just holding it here, I decide that I want to lift my arm straight up as fast as I can. It's going to shoot straight up to the ceiling and come back down. Well, it had acceleration there, didn't it? Because the force that I pushed with overcame the weight of the object. So when the net external force is some value, if my force upward is more than the weight of the object, it's going to have acceleration, which is what caused the object just to jump to the ceiling there. Okay? So again, when there's a balance and when there's no external force, the acceleration is 0. Okay, the acceleration is 0.
So if you had like a glass ceiling and you're throwing like a ball or something, would the net force be the breaking of the glass or something?
Well, here's what would happen. The glass has what's called a yield point, or a certain amount of force that it can withstand. If the force applied from the actual object you throw is greater than the actual limit of the glass's force that it can allow, it'll break it. So if the force going upward, like say it hits it with a certain acceleration and the mass is like 2 kilograms, say the force is 16 newtons and the glass can only withstand 10 newtons, it will shatter. And that's how they test things, that's how engineers test things, and they give them what are called factors of safety. So for example, you guys are all sitting in a chair right now, right? And these chairs say things like weight limit 200 pounds, weight limit 300 pounds, whatever it is, right? But in reality, these chairs can probably hold like 600 pounds. But they say the weight limit is 200 so that there's a factor of safety of 3. Because 200 to 600 is a factor of safety of 3.
Elevators can hold more people.
So elevators tell you, what do they say usually? Limit of this many
Like
pounds, limit of this
seven
people.
people, yeah.
Yeah, in reality, they could hold more, but to be safe and to watch their own back, the engineers say that. And they say, the limit is 7 people. And if you're above 7 people and you exceed the limit and it breaks, it's your fault. And that's true. They're allowed to do that. But in reality, those things can hold a lot more than 7 people. It's called a factor of safety. And traditionally, there's at least a factor of safety of 2 in engineering. So if something can withstand X amount, and they say it can, X amount, they say it can withstand only 1/2 of that, so that you don't take a chance of breaking it. Okay? It's a good question you have. Now, let's take a look at this example. When a crate is pulled to the right, I'm going to erase this. When a crate is pulled to the right with a force of 82 newtons, to the left with a force of 115 newtons, up with a force of 565, down with a force of 236. Find the net force in each direction. Okay? And then we'll find the resultant force at the end. So what I want to start is this. Please draw a free body diagram from yesterday. FBD. We want to draw all the forces that are acting on the object. On the object, okay? Okay, on the object here. So, a crate is pulled to the right. Let's start like this. Now, to the right and left, is that the X or the Y direction? X. So I'm going to call this F1X. F1X. The first force in the X direction. It also is being pulled to the left. We'll call that F2X. The second force in the X direction. In the Y direction, it's being pulled upward. We'll call that F1Y. And what is the last one going to be? F2Y. Okay? So I've labeled my 4 forces. And please, please, give them actual variable names first. Then we'll plug in the numbers. Give them names variably so that we can identify them. For example, F1X is just 82 newtons, really, right? So I could have written 82 newtons there, but I want to identify what's going on, really. All right. So I want to look at the result in each direction independently. So look only at the X first. In the X direction, what's acting to the right? How many newtons to the right? 82. 82 to the right, so we'll say positive 82 newtons. And what's acting to the left?
115 newtons.
And it's to the left, so I say
Negative.
negative.
Can that be just
So,
random?
2 is going to always be negative.
No, it doesn't say.
One at a time, one at a time. So go.
That can be random.
The names of them? If it's in the X direction, I would normally call it F sub x, meaning a force in the x. But since there were two, I distinguished between 1 and 2.
Oh.
Same thing with the y direction. You can call it F sub y, but since there's two of them, let's make sure that we distinguish. Tristan.
So 2 is gonna always be negative and 2 is gonna always be positive. Yes.
I happen to call 2 the negative values, one going down, one going up.
I just mean like 2 of the.
Oh yes, on this case, in this problem, yes, absolutely. Absolutely. In the y direction, what's acting upward? Upward, Erica.
Positive 165 newtons.
565 upward with a positive. Very good. And finally, what's acting downward? What's acting downward in this problem? What's pulling it down here? Tristan. Negative 236. Okay, again, downward is negative. To the left was negative. Remember our orientation. Left and down are both negative always. So let's sum these up. Let me move this down a little bit. Whoa. In the x direction, what do we get here? 33.
Negative 34.
Thank you. It really doesn't matter which one you call 1 and 2 now. It's up to you to decide. In the y direction, 329, I think? Does that sound right?
Yeah.
Somebody check for me, please. So here's what I want you to do next. And this is 329? Perfect. This is what I want you to think about now. The upward force overcame the downward force. I know that because my resultant is positive in the y. So this upward force here was greater than this downward force, yielding a positive answer. The leftward force was greater than the right force because I got a negative answer in the x. So if I were to draw another free body diagram that summarized my results, can somebody tell me what that might look like?
It would kind of,
Tell me this one first. Where would that look?
that would go to the left.
I'm just going to put, sorry, the board, it doesn't work in the middle. It never works in the middle. So we're going to put 33 newtons left. And I'm not putting a negative sign because the arrow already indicates left. So I don't need the negative sign there. Is that clear? Again, the left arrow indicates that it's negative already.
Is it okay if we do put it down?
I wouldn't because it might make you think negative, negative. Because the left arrow and the negative are like double negatives there. So on your free body diagram, the arrow will indicate the negative part.
Okay.
So you don't have to put the negative.
So you don't put the negative there. You don't put the negative there. I would not because it might confuse you later on when we do something else.
The box is to indicate that, right?
Yes, the left arrow already indicates that it's negative, so we don't need the negative. It would be redundant. Okay? Be careful. Pick that up. Set.
And then it would be going up at 329.
Good job. Newtons. 329 newtons. So that's the resultant forces right there, in the x and the y direction. Those are the resultant forces. Now, the other class asked me a question, and I wasn't going to do this, to be honest, but they asked the question, I think it's something good to do. How would I write this in general as one force? How do I put those two together? And how would I put them together? Yeah, very good, Erica. I need a right triangle here. Because it's going up and left, my net force is really this. Does everybody see that? If I were to lift this table up and pull backward, it would be going up and to the left, or for your perspective, up and to the right. Okay? Again, because the object is being pulled up and left, that's going to be the result. But the question is, what is its magnitude? How do I find out what the number is?
But wouldn't it be greater to the top?
It would for sure. So the angle is going to be closer to the top. So realistically, Helen, you're right. If I were to try and draw this realistically, it should probably look something like this, right? A steeper line. Because 329 overpowers the 33 by line. And that's where in Algebra 2, you're going to learn how to find out what that angle is. And that angle will tell you what the steepness will be. Okay, that's SOHCAHTOA, what you're going to do later in the year.
Oh, okay.
But if I wanted to find out what the actual magnitude is, or the number that should go with this, it's not 329, it's not 33. how about I try and figure out what it is? Erica?
Did you add big and nine in it?
Not adding. Good idea, though. I understand why you would say that.
Would it be inverse?
Would it be what?
Because you're trying to find the angle.
Very good. You like, that's for the angle, though. I'm not going to go into the angle, Sibylla. That's exactly right, though. If you're
It's
finding,
like 4 hours of terrible
relax.
term.
If you're, Sibylla, if you're finding the angle, you do the inverse sine or inverse tan or inverse cos. But we're not going to find the angle right now. I'm just trying to figure out how many newtons is it. But for the angle, you're absolutely right. Very good.
What did she say you did?
When you,
Something you guys didn't learn yet. You're learning later in algebra 2. That's why I'm not going into it just now.
so we're trying to find out the force upward to the left or the
Yeah.
overall force on the object.
So if I were to draw the diagram like this, Tom, and just drew the one force, what would its value be? That's my question. Because these two, clearly, these two make up this force right here. That's what they make up. Because it's going up and to the left, it means it's upward left. So if I were to draw it with just one force on this object, resolving all four of these, how would I figure out its value?
Can you do the average?
Not the average. Not the average. Good idea, though.
Divide.
This sounds good.
Do it like a slope, maybe?
Kind of. You're the closest so far. If I were to draw it this way, he said kind of like the slope. Do like a slope for it.
Kind of be like doing
I didn't.
The slope would be a better estimate of the angle. The slope would help you with the angle. Now, what if I drew it like this, guys? What if I drew it like this?
Yeah.
like that.
What is it?
Oh.
Yeah. Isn't that what it is, really? 33 left, 329 up. If I want to find what it actually
Oh, so
is.
it is like the slope.
Sorry?
What did you get like an insanely high number?
No, try it. Please. Try 329 squared plus 33 squared equals r squared. Solve for r.
3, 2.
Never mind 33.
Again, 33 is pulling left, 329 is pulling upward. To find the resultant vector, we can use Pythagorean theorem.
Oh.
Yeah. 330.65.
Yeah.
And take a look. It's really not much more than the vertical force was, right?
Yeah.
Helen, why is that?
Because the force pulling up is so much greater than the force pulling to the left.
Very good. The force pulling upward is so much larger than this force pulling to the left, it's almost insignificant. And when you square this number, you're going to get something in the order of 100,000. When you square this number, you're going to get something in the order of 1,000. So this number is like not even existent. So notice how close it is to 329? It's just 330.65. It only went up by a newton and a half because the 33 is very insignificant. It would be like me lifting an object almost completely vertically with a little bit of horizontal pull. Just a little bit. Okay?
You just cross out the square for that one.
Pythagorean theorem.
And then you square it.
And you get a number here. You get a number here. They equal r squared. Add them up. Take the square root. Practice your Pythagorean theorem, people. Come on, geometry.
Shouldn't it be 2 inches?
Okay?
Shouldn't it be 2 inches because it would be either positive or negative?
Yes, it would be. Very good. Very good. We take a square root. It is plus or minus. Okay? It is plus or minus. Very
Wait,
good.
so that if it was going like in the diagonal, it would be minus.
Yeah, but remember we said that the arrow is already indicated.
Would it be positive?
Yeah, but I thought.
It would be minus, and that's. But we're not going to worry too much about that now. Just because we're not looking at the angles and stuff. If we were looking at the angles, it would answer that question easily. Guys, one question at a time. Come on. Erica?
The final answer would be positive though, right?
Yes. All right, next one. Or next thing. All right, the next thing. In the past, you've heard about mass. Girls? You've heard about mass as the amount of matter or the amount of stuff, right? So if you want the mass of this marker, it's how much stuff or how much material it's made out of, which is fine. And that's the definition I give right here. Or the amount of matter, matter being stuff. I know it's not a scientific word, but that's what it really is, okay? Now, the other way of thinking about it, which is a little more confusing, but I'm going to make it very clear for you, is the measurement of inertia. And I'll explain this now. Okay, I'll explain this. Write it down. I'll give you a second to write it down. So the new part is what's boxed in red there, a measurement of inertia. Now, here's my question for you. First of all, remember what inertia says. Think about the first part. An object at rest wants to remain at rest. Right? We all agree with that?
Yes.
So, if I were to go to the driving range and want to play some golf, and I set up a tee with a golf ball, and the other tee I put a baseball. I put basketball, it doesn't really matter. So we have a baseball on one tee and a golf ball on the other. And I try to hit them both with a golf club. The golf ball is probably going to go, like 250, 300 yards, right? Anybody play golf here? Okay. Mini golf. Putt. All right. So golf balls, if you hit them with a driver, will travel, between 200 and 300 yards. And if you hit the thing with a baseball, if you hit a baseball with the same thing, what's going to happen then?
It's gonna go not as far.
It's not going to go as far at all, right? Think about it. Try to hit a baseball with a golf club. It might go, 20, 30 yards, but that's it. The reason is we say, well, the baseball is heavier, or the baseball has more mass, we say usually, right? Or the baseball has more inertia. It has more of a desire to remain at rest.
Why is that?
And think about it for a second.
Heavier.
The baseball is made up of more matter, so sure, it's heavier, but its inertia is higher. Its inertia is higher. Its inertia is the amount of, the desire for it to stay at rest. So the inertia of this clicker or remote, whatever it is much more than the inertia of this piece of string here, right? I mean, look at the difference here. If I were to push this piece of string, if I just flick it with my finger, see how far it went? And I put the same force. See how far that went? The inertia here is much greater of the clicker than it is of this piece of string. So the clicker wants to stay at rest more than the string does. So since its inertia is greater, we can also say its measurement of inertia or its mass is greater. Okay? Again, mass, you want to think about how much would it take to move the object. If it takes more to move the object, it's got more mass. It's got more inertia. If it doesn't take much to move the object, it's got very little mass or less measurement of inertia. Okay? So you can think of inertia, its measurement, synonymous with mass. So if you said an object has more mass, it's got more inertia. If it's got less mass, it's got less inertia. Okay? They're almost interchangeable. That's why I'm calling it the measurement of inertia.
With this insertion concept, I don't know what that is.
I don't understand what you're saying.
Like, what is the inertia? Just like an object that wants to stay at rest.
The desire of an object to stay at rest. So this book here, it would take a lot more for me to move this book than it will to move this piece of paper, right? And in the past, you would say because it weighs more. I'll tell you because it's got more inertia. It's got more desire to stay where it is than the paper does. The paper's free to move because it doesn't have a lot of mass or a lot of inertia. This has a lot of inertia. It wants to stay where it is more than that does. You're giving it almost, it's personification, right? Remember the literary element of personification? You're giving a book a personal quality or a human quality when in reality it has no desire to stay there, but that's how we can think of it. Okay? All right. Let's go on to the next thing. Oh, okay. Just listen here. Just listen. You don't have to actually write anything down. This is a good example of mass and where it's used. Now,
What is that?
I'll explain. Relax. A lot of you might think you're in a car. So imagine the situation. You're in a car, and suddenly you see that there's an accident up ahead. So what are you going to do?
Put your seatbelt on.
Well, assuming your seatbelt's on, like you always do.
Okay, I have a question. You know when slow down, slow down.
Kind of stop.
What's the reason for that? Closing the
Relax. Have patience. The saying in Italian is "Abbia pazienza." Have some patience, please, please. It will come up.
Are you trying to show off again?
It's the same my mom would use nothing.
You are a
So,
worldly man.
If you're driving a car, again, the question was, when you see an accident up ahead, what do you have to do?
Slow down.
Slow down, right? Come to a stop. So you apply the brakes. Now, when you apply the brakes, the question is, how come the seatbelt locks in place when you apply the brakes? And this will always happen. When you apply the brakes, the seatbelt's going to lock so that in case you go forward, the seatbelt will stop you. And I'm going to explain to you how it actually works now. And it's a little bit different than what people think. Everybody thinks you hit the brakes trigger the lock in the seatbelt, which is not actually true at all. Okay, this diagram is going to explain it.
Nope.
Helen?
Wait, isn't it like when you pull it really fast, like it locks because it thinks that you're like getting thrown at the sea? But wait, why does it that hurt you
You
more?
answered your own question, and now you're asking another question.
I literally think that like breaks your ribs. I think if I was actually an accident, I would like break my ribs if the seatbelt did that.
I'll take a
Do you ever,
broken
like, get
rib
that?
over going through a windshield and into the next car.
I guess actually. Yeah.
It's like the airbags, guys. Airbags hurt you. You do get hurt from an airbag, but you know what? You die or you get a little bruise. Which one you want? Right?
Wait, you don't get.
Airbags, you can, yeah, absolutely. The
Wait, but
force
if you're
from an airbag
pregnant,
is very
wouldn't the
expensive.
airbag, like,
And airbags also can burn you. Sometimes you get rashes from an airbag.
Why?
It's just the way they're built.
The blinds up.
All right, let's focus. Let's get back. Let's get back. Steph, give me 1 second. I'll answer your question. I want to explain how this works.
I thought I had the answer.
Wait,
Oh,
yeah, it's
go,
when
go.
you pull it really fast.
Guys, listen. Come on. Steph.
Is it that the seatbelt doesn't like react to the brakes being hit, but it reacts to the inertia
Yeah,
that
very
you
good.
put on it?
You
So
go wrong.
if you go slowly, you're putting less inertia on it.
Okay. Or you can think of the car's inertia is changing by less. So the car's velocity. So here's how it works. Ready? I'm going to go through this diagram here with you. It's very simple. It looks complex. It's so simple. Here, underneath the seat, as part of the base of the seat, there's a mass, some object, and it'll usually be a block. This block can slide forward and back. Now, before I go into what happens, think about the subway. You're on the subway. You're standing still. The subway is at rest. Suddenly, the subway starts to move. Guys, come on. Suddenly, the subway starts to move, right? When the subway starts to move, you get that feeling where you get like pulled back, right? And then when the subway comes to a halting stop sometimes, when you get to your stop, you feel that fall forward feeling. Same thing in a car. You hit the brakes, you feel like you're falling forward, and the seatbelt catches you. So here's what happens. The brakes are engaged in the car. This mass slides forward, like this, so that now the mass is located here. When the mass slides forward, it's attached with a pin connection. It's attached to a rod. The rod then rotates. So if this mass is pulled forward, now the mass is here, and now the rod is at an angle. Instead of before, it looked like this. There was a pivot point right here, and now there's a pivot point right here. So when this mass pulls forward, the rod is going to pivot. And that's this, you see this like faint rod behind it at an angle? The rod now pivots about this pivot point. That's the pivot point right there.
That's
Because
so
again,
cool.
the mass is connected to the rod with a pin connection here. When the mass slides forward, it pulls the rod, which causes the rod to turn like that. Now, the rod then in turn engages what's called the ratchet. This ratchet has these little teeth on it. When the rod engages the ratchet, it stops the ratchet from rotating. When the ratchet can't rotate, the seatbelt can't rotate on the conveyor belt, so it locks it shut.
That was actually sometimes we try to pull the
That is
seatbelt.
what
Yes.
Yeah, that's what this whole
Yes.
Why would
It's
you
the same
want
thing.
it?
Some guys,
Yeah.
sometimes when you pull on the seatbelt, it'll engage the ratchet inadvertently. It won't do it because of the inertial force, but it's because of the way you pulled on it. Okay? And then what do you have to do? You have to let it go.
Yeah.
It disengages, and then you can pull again. Okay? If you're interested, if you think this is intriguing, I'm telling you guys, this is what engineering is all about. You take a look at a small system, and you look at all of its components. I can analyze every force on this, the force on the pins, the force on the pivot, how much this gear train is moving. And you can then set it up to do this. This is what engineering is all about. Okay, so if you think this is intriguing at all, you might want to consider that as a, profession. All right, last thing to do. Last thing.
Is that
We're not going to get to the last part of the lab, unfortunately, but what I'm going to do is after school, I'm going to solve one of the lab questions, and I'm going to post a video for you to watch. So remember the lab part 4. There are 3 questions on there. 3 mathematical parts to part 4. I'm going to solve a sample problem and post it online as a video for you guys to watch to help you finish the lab over the weekend. Is that clear? Okay, because we're going to run out of time to do that. Now, equilibrium. What word is in equilibrium right away? What do you see? Equal, equal, equal. When you have equal, you think of both sides of the equation as being the same. So in physics, equilibrium is like the forces are the same. So imagine if me and Helen decided that she's going to pull on that side of the desk and I pull on this side of the desk. And if we both pull at the same force, is the desk going to move?
No.
Because it's the same force. It's in a state of equilibrium.
Oh, it's like
But if
tug of
Helen
war.
overpowers me, pulling that way, what's going to happen?
The desk's gonna come down.
It's going to move toward her because her force is greater than mine. So equilibrium is just about a balance of forces. Now, that's all it is, a balance of forces. The definition is a little different. The state of which the net force on an object is zero. That's what we just said. Or there's no change in the body's motion. There's no change. So either the object is at rest and it remains at rest, or we have an object moving with a constant velocity and it's not accelerating at all. So let me give you some quick things. First, equilibrium implies three things. Three things. The sum, that's a sigma sign, it means the sum of, I think I've used it once before, maybe here earlier. The sum of all the forces acting on the object is zero, and that's the balance, me and Helen pulling back and forth. Her force is 50 that way, mine is 50 this way, the net force is just zero. So the sum of the forces is zero. Again, in the x and y, give me 2 seconds here. If the sum of the forces is zero, the object's not going to move, right? So the acceleration is also zero. And the last part is the tougher part to know. The velocity is a constant. It doesn't necessarily have to be zero, because the object could be moving at a steady rate. When the object is moving at a, listen before you back up, when the object is moving at a steady rate, there's no acceleration. So no acceleration just means that the velocity is constant. The velocity could be zero, but we know that it's constant. So this weekend, here's what you're doing. These 3 problems. Now I told the other class, it's up to you guys to do. But we've done 4-1 and 4-2. When we get back on Monday, we're doing 4-3. You might want to just read over the notes in the textbook. Spend a day, 10 minutes each day. Okay? Finish your lab. And I'm not going to make it due on Monday when you get back. Okay? We're going to say it's going to be due on Wednesday. Okay?
Put this on Moodle, right?
And you're going to see a video on Moodle. Okay? I'll put the homework on Moodle, obviously. Okay? But watch the video on Moodle to help you with the lab.
Wait, Mr. Howell, you're putting all our homework on Moodle.
Yes. Remember, if I didn't get your problem set today, it's due tomorrow, and that's 1 day late. Don't wait any more days.